sine r squared times r? Okay, quick way. If this problem is in your calculus 1, you probably notice that this r comes from derivative of r squared, right? Derivative of r squared is going to be 2r, so that's related to the r squared. Therefore, you can use u substitution method. Typically, you're going to let u be r squared, right? And then go from there. So if you're familiar with that, you know, the whole thing, this r comes from sine r squared. This part is sine u. So antiderivative would be negative cosine u in general. Negative cosine u. And think about it, what is going to be the derivative of this portion? Derivative of negative cosine r squared, if you think about it, it's going to be sine r squared and times 2r, right? And there's no 2 here, so we should divide by 2 to get rid of that 2 for the antiderivative. So antiderivative is going to be negative cosine r squared over 2. Okay, r, the radius r, evaluated from 0 to 1, and then d theta. The d theta and 0 pi over 2 is still in the outer layer. They are still there. Okay, we're just doing the inner layer. Okay, continue. So from 0 to pi over 2, and let's just evaluate a 0 and a 1 in. Okay. First of all, let's plug in 1. So we have negative cosine 1 over 2. And subtract, we plug in 0. If you plug in 0, I have negative cosine 0, which is negative 1 over 2 d theta, right? All right, so this is just 1/2. If you simplify this piece, I have negative 1, which is 1 minus cosine 1. This is a constant, right? A constant. Its antiderivative with respect to theta will just be theta, and then theta goes from 0 to pi over 2. So in the end, if we plug pi over 2 and plug 0 in for the theta and evaluate it, it's just going to be 1 minus cosine 1 over 2 times pi over 2, which is just pi times 1 minus cosine 1 over 4. Okay? So in this question, we have converted x squared plus y squared to r squared. Dx dy converted to r dr d theta, and radius r goes from 0 to 1, and the radius angle theta goes from 0 to pi over 2. After that, you just do the iterative integration evaluation from inside to the outside. Here, the inner integrand is sine r squared times r, where r comes from derivative of r squared. Okay, so you can use the regular u substitution for its antiderivative. Any questions? All right, and then we're going to move on to the next topic for the section. The section we have another topic which is pretty important that we can evaluate is called the area of polar region. Okay, area of polar region. So basically, we're trying to find area. Okay, find area. Those areas are in polar region. When we are introducing double integrals, we have talked about this important conclusion. We said double integration of a constant k. K is a constant k. You can pull the k out, and you get double integral of region R, 1 dA. And we've said this double integral of region R of 1 dA is area of region R. So this is what we're going to use today here. So we're going to use this double integral over region R of 1 dA is the same as area of region R. So this formula helps us to find area of region R. Okay. And this could be both used in both Cartesian system or polar coordinate system. So really depends on the construction of your area. If it's easier to describe in Cartesian, you can just use Cartesian for double integration. If it's easier to describe in polar, then we can use the polar description for the region R. So here it comes for area of polar regions. Okay, polar regions. Suppose the region R is a R simple region. But the same method can be applied to theta simple. Theta is bounded between two constants. Then area equals to double integral of 1 dA, which is double integral of dA is r dr d theta. And your radius r has two boundaries and theta has two boundaries. Okay. So in general, in short, we'll just need to make the integrand to be 1 and convert dA to r dr d theta as we have seen before. So let's take a look at this example 6, area of region. Evaluate the double integral by finding the area of region. So let's take a look at this double integral. We have double integral from 0 to pi, 0 to 3, r dr d theta. Okay. So this one basically, because the integrand is 1, this is just the same as 0 to pi, 0 to 3, 1 dA, right? Because r dr d theta is dA over region R. Okay. So we know this double integral should be just the area of region, okay, area of the region. So now the question is, what is this region, right? What is this region? So region can be described by looking at your R. The radius here, R, is between 0 and 3. Theta here is between 0 and pi. Okay? So can you guys try to sketch this region R with these two informations? Radius is from 0 to 3, angle theta is from 0 to pi. Can you try to sketch the region? Okay, this region should be hard. This is about the polar axis, right? Angle theta is from 0 to pi, so 0 to pi. Here is pi. The radius starts from 0, ends at 3. So suppose this is 3. You're going to have a radius of 3. This part, and then keep going to -3. So radius goes from 0 to 3. It covers this whole inside of the semicircle. Okay. So that's going to be our region R. Okay. This is the region R. So once you see this region R, it should be very easy to calculate the area, right? Because that's just half of the area of the circle. So it's half of area of a circle, which is going to be 1/2 of pi r squared. Pi r squared. Over here, the radius r, easy to see, the radius will just be 3. So pi r squared. Therefore, this will just be 9/2 pi. Okay? Okay, guys. So far, so good? All right, if this is fine, I'm going to move on to the next question. So next question is similar. Evaluate the double integral by finding the area of the region. We have integral from 0 to pi over 2, 0 to cosine theta, and then you have r dr d theta. Okay, r dr d theta. Remember, this is just dA. And this part could just be written as over region R. So this is again double integration over region R times dA. And we know this is area of region, okay? So the question will just be, let's sketch the region R and then find its area. Let's go ahead and see. We have radius. First of all, let's discuss the radius. Radius is between 0 and cosine theta. Theta is between, read the theta. Theta corresponds to the outer layer. So theta is from 0 to pi over 2. Okay, so let's see what kind of region this is. Okay. So first of all, it's easy to see the theta. Theta is between 0 and pi over 2. So 0 and pi over 2. It's going to be in the first quadrant, right, from 0 to pi over 2. Second, radius is from 0 to cosine theta. So 0. When radius equals 0, it's referring to the origin. So it starts at the origin. And secondly, it should stop at r equals cosine theta. Okay. What's the graph of r equals cosine theta? This one you should have learned in calculus 2, when Dr. Tyrbach introduced the polar system, right? R equals cosine theta, you can get its graph. And the way for us to look at its graph is try to convert that to Cartesian, to x, y. So we'll have to get a r squared and r cosine theta. Very easy, let's just multiply both sides by radius r. So we have r times r equals r times cosine theta. All right, by doing this, we have r squared, which is x squared plus y squared. And r cosine theta is going to be x coordinate. So this is just x squared plus y squared equals x. And you can move the x to the left-hand side. We have x squared minus x and plus y squared equals to 0. All right. Now, it's easy to see that this is going to be quadratic and plus a quadratic. So eventually, this is going to be a circle. However, where is the center of the circle and what's the radius needs to be computed in the next step. And this one is called complete the perfect circle. We've done that before. Complete the perfect circle, perfect square. So let's see how we complete the perfect square. So we should have x squared minus x and add a value here. And subtract the same value. And here plus y squared equals to 0. This amount we have to intentionally add comes from the coefficient of x. Coefficient of x is -1. So we're going to divide by 2 and then square that. So half of the coefficient and square that. And this amount you have added is actually 1/4. Right? 1/4. So we should subtract 1/4. Once you do that, you would have x squared minus x plus 1/4. Okay, which if you do factorization, you would have x minus 1/2 squared, which is a perfect square. And this is another perfect square plus y squared equals to, I'm going to pull the 1/4 to the other side, plus 1/4. So now you can see that this is absolutely a circle, okay, whose center is going to be at 1/2, 0. And radius is going to be square root of 1/4. So radius is going to be 1/2. All right, so if you sketch it, basically the center should be at 1/2, 0 on the x-axis. And the radius is 1/2. Radius is 1/2. So this is going to be a circle, right? A circle. This is the circle. The radius r should be ending with. So if I sketch the radius r, it first intersects a 0. Second, it should intersect this circle. And secondly, don't forget about the theta. Angle theta starts at 0. Okay, so starts at 0, ends at pi/2. With these information in hand, this is the constraint of angle theta, and this is the constraint of radius. We can tell the area of region R would be this shaded area. So this would be my region R, which happens to be another half circle, okay, inside of the semicircle, okay. So area of the R would be pretty easy to compute based on our previous knowledge. It's going to be 1/2 of pi r squared. So that happens to be 1/4 divided by 2, 1/8. So it'd be pi/8. Okay. So again, for this problem, we recognize r drd theta is just dA, and integrand is 1. Therefore, this double integration is actually asking you for the area of region R. Okay. All right, the next question, example 8, is we are actually finding the area of region. So let's find the area of the region S by double integration. S is the smaller region bounded by theta equals pi/6 and R equals 4 sine theta. Okay, so there are two regions. One is theta equals pi/6, one is R equals 4 sine theta. We need to sketch both of these two graphs and find the region S. Okay, find the region S. The first graph, theta equals pi/6, is relatively easy to sketch. It's just going to be a straight line, okay, theta, because angle theta is pi/6, so that's almost 30 degrees. This is going to be theta equals pi/6. The second graph we need to sketch is r equals 4 sine theta. You may have noticed that this is similar to the one we had in example 7, where r equals cosine theta. Now it's r equals 4 sine theta. So we need to do the similar conversion from polar to Cartesian for us to better look at the graph. All right, so we're going to do the conversion. Convert to Cartesian xy. Same approach. We start with r equals 4 sine theta. Let's multiply by r both sides. This is r squared, which is the same as x squared plus y squared. R sine theta, we know that's y. Okay, move the 4y to the left. And then we're gonna complete the perfect square. And this time we should have half the coefficient, which is -2. Square that, that's gonna be 4. So you added 4 in the left-hand side. So you can add 4 to the right-hand side to balance it, okay? We have x squared plus y minus 2 squared equals to 4, which is another circle, right? Whose center could be found looking at x and y minus 2. So center would be 0, 2, and the radius is going to be square root of 4, which is 2. Okay. So I'm going to go ahead and sketch this graph over here. So it should be a circle. Here's x-axis, here's y-axis. This is circle center as 0, 2. 0, 2 is on y-axis, so 0, 2. Let's suppose this is 2, okay? And the radius is also 2. So we should go to the right for 2, down for 2, left, I'm out of space there, but what matters most is this piece. And you can tell it has upper part. And then it continues to the left, and it continues to the left here. So this is r equals 4 sine theta. All right, so we have first graph, which is r equals sine theta. Second graph, theta equals pi over 6. Can you guys see the region that's bounded by these two? It should be pretty obvious. It's a small, tiny region, right? Trapped between the straight line and the circle. So it's going to be this region here. Okay, this region in green is going to be our region S. This region is just a tiny piece of part of the circle, and we don't have any existing formula to compute the area of the region S, so we'll have to do area of region S. Let's use double integration. So it'll be integral over region S and dA, which again, dA a lot of times is going to be r dr d theta, right? Dr d theta for this region S. Okay, next let's think about how do we describe this region S by using polar coordinates. Okay. Polar coordinates, I'm going to, first of all, we need to make sure whether this is r symbol or theta symbol. Okay. For this region in light green, we can tell it's bounded by theta equals pi over 6, and here, which is theta equals 0. So theta can be controlled by two constants, right? So it's not going to be theta symbol. We should just consider r symbol. Okay, let's sketch a radius going from origin and intersect this region R. We can tell it first intersects the origin, and secondly, it intersects the piece of the circle. So the radius can be controlled by two functions. One is 0, one is this function, which represents the circle. Okay, so that's going to be r symbol. So our S region could be described as theta between 0 and pi over 6, 0 and pi over 6. Radius starts at 0 here, ends at this circle. Circle, we know its radius equals 4 sine theta. So 4 sine theta will be its upper bound. Okay, with this in mind, we can write our double integration here. So double integral r dr d theta. Okay, radius r goes from 0 to 4 sine theta. Theta goes from 0 to pi over 6. Over next will just be the evaluation of this double integration. Okay, let's continue in the next slide. So 0 to pi over 6, 0 to 4 sine theta, r dr d theta. Okay, so first of all, let's do this inner integration. Okay, so here we have 0 to 4 sine theta, r dr Antiderivative is easy. It's just going to be r squared over 2. And r goes from 0 to 4 sine theta. Okay, let's plug this in for radius. So we have 4 sine theta squared over 2 minus 0, which is going to be 16 sine theta squared divided by 2. That's 8 sine theta squared. And we know sine theta squared could be expressed by using half angle formula or double angle formula, right? Double angle. So double angle formula will give it 1/2 1 minus cosine 2 theta. In this way, you can take care of the square, sine theta squared, to a just a regular cosine function. So I'm going to write this as 4 times 1 minus cosine 2 theta. All right, so that's going to be the inner integral. The inner integral will just be 4 times 1 minus cosine 2 theta. All right, over next, we can just get the outer integral. Okay. Therefore, the outer integral, which is the area of region S, will just be 0 to pi over 6. Replace the box by this part, 4 1 minus cosine 2 theta d theta. Constant 4 could be pulled to the front. 1 minus cosine 2 theta, antiderivative will just be theta minus cosine 2 theta, it's antiderivative. So sine 2 theta over 2. And theta goes from 0 to pi over 6. Okay, well, let's go ahead and plug pi over 6 here for theta and plug 0 in for theta. When we first plug in pi over 6, I should have pi over 6 minus sine 2 times pi over 6, which is pi over 3. And divide by 2. All right. So that is 4 times pi over 6 minus sine pi over 3 is sine 60 degrees, which is root of 3 over 2. So root of 3 over 2. And further divide by 2, right? So that's 4 times pi over 6 minus root of 3 over 4. Okay, over next you can either distribute the 4 or just leave it like this, that's fine, okay. But anyway, this fraction, okay, this expression is just the area of that little piece in green. It's gonna be this area. So it's the area bounded between theta equals pi over 6, which is a straight line, and the circle r equals 4 sine theta. Okay. All right, so that's the end of this section. Let me check with you guys. All right, Jonathan, any questions? Okay, Jonathan and Mary. All right, so that's gonna be this little piece for polar coordinates. Let me see, I'm gonna exit this slideshow and keep all the annotations. Over next, we're gonna talk about a new section, which is pretty short, okay. So we're gonna just cover it here. Share. Can you guys see my screen? Folks, can you see my screen?
Yes.
Okay. All right. Yeah, thank you, Donovan. All right, so we're gonna talk about this short section, which is 13.6, surface area. Okay, surface area. This is a pretty short section, so we can finish this real quick. Oopsie. Somehow, let's close this. So surface area, the goal of the section is to talk about how do we use a double integral to find the area of a surface. Okay. You probably already know some area of surface, and kind of like a surface area of a sphere. Okay, sphere is 4 pi r squared, if you know this formula. Okay, so if you know if you get a sphere, right, so the surface area would be 4 times pi r squared. Okay. But this section talks about, in general, if you have a surface, how do we use a double integral to find its area? So this is the general graph. Okay. We already know a lot. Okay. We already know a lot about a solid region lying between a surface and a closed region R. Suppose this is region R. Here is a surface on top of it. Okay. We can use double integration to calculate a lot. For example, we can use partial derivative to find the extreme values over the surface R, right? Extreme value. Find extreme value on R. We can also find the area of region R, which we just talked about it. Area of region R can be computed by double integral dA over region R, right? We also talk about how do you use double integration to find the volume of the solid, right? Volume of the solid. The centroid of the base is centroid of the base is related to physics, so we didn't really talk about that, but if you're interested, you can also look into that. These three are the ones we have talked about in our class. Extreme value of the function f, so maximum and a minimal, right? Maximum and a minimal. Area of this region R, which is double integral dA over region R, and is the volume. So volume here would just be double integral of function f dA over region R. So you change the integrand to the function in order to calculate the value. So these three items, we've already talked about it. Next, we want to talk about how do we find the upper surface area of the solid. Okay. So let's consider we have a surface as given by z equals f of xy defined over a region R. Let's assume region R is closed and bounded, so all the boundary points is in R. Function f has continuous first partial derivatives. So f is differentiable, right? Differentiable. So basically, this is the graph. So we have a surface over region R. We want to know what's going to be the area of the surface. Okay, area of the surface. Very similarly, we're going to use a Riemann sum. Okay, Riemann sum. But first of all, you're going to construct an inner partition of region R, as we do all the time, right? You got to partition this region R into small subregions. The easy way is to decompose them into small rectangles. Okay, small rectangles. So suppose I have ith rectangle. Okay. This piece is ith rectangle. Its area, okay, the area of this rectangle will just be the length times the width. So how much on the x direction and how much on the y direction. So delta xi times delta yi. Once you picked a subrectangle, you're going to pick a point, a representative point. Suppose xi, yi is the point that you picked. Then with this point, we can go back to the surface and find the corresponding point, okay, matching this xi, yi on the xy plane. So this is going to be the matching point. So this point is going to be xi, y, yi, and z sub I, right? Now, because this surface is differentiable, we know you can construct a tangent plane, the tangent plane. So here is the tangent plane. Okay, this part in blue is going to be its tangent plane. The tangent plane happens to touch that point, and also touch the surface only at once. So we have a tangent plane, T sub I. Next slide, let's look at this tangent plane and closely with the surface area we want to calculate. So the area of the portion of the tangent plane that lies directly above r sub I can be approximately equal to the area of the surface lying directly above r sub I, which means if you decompose the surface area into small pieces, each small piece of the surface area, surface area would be approximated by the area of the tangent plane. So these two areas, okay, you can look at this area, small area of the surface, and the area of the tangent plane. When they are small enough, they should be pretty close. So delta SI can be approximated by using delta TI. T indicates tangent plane, so the area of the tangent plane. And once you add it up, the total area is total area of the surface, which is just the sum of all the delta SI, can be approximated by the sum of all the tangent planes. So the question is, how do we calculate area of the tangent plane? So area of the tangent plane. Now the tangent plane can be considered as a parallelogram. Okay, if you look at this delta TI, parallelogram, right? And this will just be our delta TI. Because it's a parallelogram, so it has two sides, right? This is one side, this is another side. One is on the x direction, and one is on the y direction. Okay. And each of these two sides could be represented by using these two vectors, okay? One is on the x direction, one is on the y direction, okay? U and a v. And we have talked about before, area of the parallelogram can be computed by using, if this is u and this is a v, can be computed by using the magnitude of its two sides. So u cross v. When we are looking at vectors, you guys probably remember that. Area of the parallelogram is magnitude of the cross product of the two sides of the vectors. All right, so I'm just going to do that. Vector u is on the x direction, vector v is on the y direction, and we're doing u cross v. Okay, u cross v, finding its magnitude. So this is going to be the u cross v. Its magnitude will just be the magnitude of this vector, right? Magnitude of this vector. So it's going to be square root of sum, okay, squared plus squared and plus squared. So we have square root of partial x squared plus partial y squared plus 1 delta a sub I. So the surface area will just be the sum of all those delta SI. Therefore, it's going to be sum of all of that part. Okay, square root of 1 plus partial x squared plus partial y squared times delta AI. Let me go very quickly go back to our original graph that we had over here. So what we are talking about is basically you're decomposing the surface area based on your region R here. Each small rectangle in the region R would match a small part of the surface area. So for this part, it will also match a small surface area, right? So eventually we're just adding all those areas up to approximate the total area of the surface. The total area of the surface will just be sum of all those delta S. Okay. Which is what we did over here. So it's going to be sum of this formula, square root of 1 plus partial x squared plus partial y squared plus delta AI. And later on, we know for the Riemann sum, this is kind of the Riemann sum, so we can actually, if you push the n goes to infinity, let's suppose there are infinitely many rectangles of the region R. We can push this to limit and approaches infinity, then this total area of surface S would be a better estimate. Okay. So S would be double integral of square root 1 plus partial x squared plus partial y squared, and delta A just converts to dA. So we're using the same approach from the Riemann sum to double integral. Okay. In general, you just need to remember this formula here. Area of the surface equals double integral of square root of 1 plus partial x squared plus partial y squared dA. Okay. Over the region R. Okay. So this is the only new formula we are introducing in this section, okay, surface area. The only thing that has changed is the integrand. Okay, integrand is root of 1 plus partial x squared plus partial y squared dA. Right before we go to the one last question we have in this section, we want to kind of try to connect single integral to double integral to see some similarities. When we are doing single integral of dx over AB, this calculates the length of that line segment, right? So here is x from AB. So this integral AB dx calculate the length of AB. For the arc length in xy, you probably learned this formula in parametric equations. So integral from AB ds, the formula will be integral of AB root of 1 plus derivative of x squared dx. So that's the arc length, talking about the length. All right, now if the integrand remains to be 1, then we just talk about the area in xy plane. Double integral of region R over region R of dA, this equals to area of region R. So integrand here, they all equals to 1, right? So now we're looking at the surface area in space. So that's double integral ds over region R, which the formula converts to double integral over region R square root of 1 plus partial x squared plus partial y squared dA. That's just in one extension from the arc length to surface area. So root of 1 plus f derivative of x f squared to 1 plus partial x squared plus partial y squared dA. Extending from one dimension x to two dimension x and y's. Okay, so these are a lot of similarities between single integral and double integral. Double integral. You can also look at it in this format. Okay, when it's dx matching dA, both talking about area, and then from ds to ds when it comes to surface and arc. Now, this is the formula we have now that we need to focus on. So let's use this for our example here. Example 1, the surface area of a plane region. Let's find the surface area of this portion of the plane, z equals 2 minus x minus y, which is this straight plane that lies above the circle, x squared plus y squared less than or equal to 1 in the first quadrant, as shown in figure 3. Okay, so here we know x squared plus y squared less than or equal to 1. That's basically inside of a unit circle, right? Inside of a unit circle, here is 1, negative 1. It's in the first quadrant, so this is your region R, okay, which is over here. This is region R. And the straight plane lies above the xy plane. And correspondingly, this piece would match this piece on the straight plane. And this part of the region R would match this part on that straight plane. And here, y-axis would match this part if you try to simply project it. So this is the surface S lies above the region R. All right, surface S. We're trying to find what is the area of surface S, which we know surface S, its area could be computed by the new formula we just computed, we just learned, square root of 1 plus fx squared plus fy squared dA over the region R. Okay. Okay, yeah, we can just write the area of the S will be S. The z equals 2 minus x minus y. This is our f of xy. So function is 2 minus x minus y. So with this function, it should be pretty easy to find partial x and partial y. Let's see. So partial x would be negative 1. And then partial y would be negative 1. So these two happens to be constant, right? It should be easy for us to evaluate this double integral. So we should have double integral over region R square root of 1 plus partial x, it's square, so that's 1. Partial y, it's square, that's another 1, dA. Now we can see that in this question, the integrand happens to be root of 3. So again, we can pull this root of 3 to the outside of the integral. So this root of 3, double integral dA over region R. Okay, let's continue. This root of 3, double integral over region R dA. All right, folks, this item comes up again. It's the one that we just talked about, right? Integrand being 1. We know this is just the area of region R. Okay, so it's area of the region R. And region R is what we just looked at here. The region R happens to be a quarter of the circle, right? Inside of the quarter of the circle. So this is region R. Its area should be pretty easy to compute. Should be 1/4, a quarter of the total area of the circle. So pi, radius is 1, R squared. So we have a quarter root of 3 pi. So it's root of 3 pi over 4 as, okay, as the total area of the surface S. Okay. So I've attached the solution here, over here. So again, S would be double integral root of 1 plus partial x squared plus partial y squared dA. Compute both of that, you get negative 1 squared, negative 1 squared. So we get integral of root of 3 dAr, which would be root of 3 double integral dA over region R, which will be eventually root of 3 times area of R. That's root of 3 times pi over 4. Okay. All right, so this is the section of 13.6. This is a very short section. Okay, just one formula. You have to you know how to calculate the area of the surface above region R. Okay. Let's stop by here, guys. And next time we're going to continue on Wednesday, talk about triple integral. Okay. Any questions?
No.
Okay, thank you, Donovan. Feel free to let me know if you have any trouble, okay? I'm going to upload this video again on the YouTube and as well as the PowerPoint slides. All right? Then I'm gonna see you guys on Wednesday. Thank you.
Thank you.
Let's see.